Hi, I'm Pablo Romero and I'm presenting GCM 111 Assignment 2 on holographic printing. Starting from the top, the term hologram was coined by Denis Gabor in 1947, meaning whole picture or message. Unlike a photograph that captures the intensity of the light, a hologram is a physical recording of the entire light wavefront. This is possible using the laser coherent light to capture both the intensity and the phase information of the light waves. Phase of the light is the timing or position of the light wave within its cycle. The recording process exposes the silver halide on the holographic plate and captures a microscopic interference pattern. After this process, the plate diffracts light, allowing us to see a 3D object. Holograms are divided into reflection and transmission, depending on the trajectory that light has to take. If we see the light reflecting on them, it's a reflection hologram. However, if the hologram needs a backlight to pass through, it's a transmission hologram. The most common type of hologram in graphic communications are reflection holograms. This process happens at a really small scale. It physically changes the path of the light. The wavelength of visible light goes from around 400 to 700 nanometers, and the peaks and valleys in a hologram go from around 100 to 500 nanometers. Just to give an idea, one hair is approximately 80,000 nanometers in width. Denis Gabor came up with the theory of a hologram in 1947, but due to the lack of coherent light, meaning a laser, he was unable to make progress. The laser was invented 13 years later, in 1960, by Theodore Maiman at the Hughes Research Laboratories in California. After that, using Gabor's research and Maiman's technology, several researchers like Denis Yu, Leet, and Upatniks developed practical hologram capturing techniques. In 1968, Stephen Brenton's rainbow hologram was the next big step for holograms, as it made them bright and visible through white light. This made holograms more accessible to the public. The final steps for mass production were in the early 90s, with the dot matrix allowing for complex computer-generated holography to be printed into a master plate, and embossing allowed the master plate hologram to be replicated, making mass-produced copies cost-effective for widespread use in print and packaging. In graphic communications, holography can be used as a decoration, or even as a safety measure in packaging, but mostly it can be used as a security measure. By embossing a film with a holographic texture, we can make IDs, money, and important documents harder to counterfeit. One example I found is a research by Blau 2020, which he used a hologram that projected a readable QR code with a unique speckle pattern, similar to a fingerprint. The QR code was projected when shined by a laser. Even using the same technology, a special code is needed to authenticate the speckle, with a failure rate of 35% if you didn't have the special code. Besides graphic communications, holograms are used for archiving cultural artifacts by capturing them and having a 3D archive of the model. In the future, holograms might be used for storing massive amounts of information. One example I found is a recent article by Wang and colleagues in 2024 demonstrating how advanced techniques allow them to encode 55 independent patterns onto a single holographic element. This could lead to a great amount of information saved in a surprisingly small image. One of the biggest limitations of holograms is also the main reason for its safety. The equipment to make holograms is rather expensive and extremely precise. This cost gap is likely going to decrease as the technology advances. One example I found is a mastering equipment like a dot matrix machine, costing around $35,000. On the other side, we have LeadHolo, who developed a new 3D desktop hologram printer costing less than $2,000. This printer might not be used to counterfeit, but I believe that as time goes by, this technology will be more accessible, so security research should be a priority. With the arrival of AR and VR, the use of holograms as a way to display 3D objects might not be the most important features of the holograms. However, the advancements in nanotechnology and improvements to the quality of engraving using lasers for security measures, like the research of Blau, is one of the key aspects that we should keep in mind. The graphic communication industries could benefit from this advancement in nanotechnology, leading to an ever greater gamut of colors for holograms, as well as more cost-effective productions as a spillover benefit from the research and security. However, even if it's more affordable and advanced, the cost of manufacturing machinery is very high, so it might not reach graphic communication industries for a while. Holograms are a really interesting topic, with unbelievable small technology and incredible advancements that I believe will continue to impress us as research continues. Thank you for your attention.